Hi everyone. So I had a request from someone in the class for a little bit more help on these types of problems where you have to take the derivative of a more complicated function and kind of figure out, what rules to use and in what order. And so I figured I would just make a video going over this worksheet because I think this is a topic that a lot of students struggle with. And so I just wanted to go through a few more examples, and I'll probably bring up a couple of examples along the way to kind of contrast with the ones here, and try to just, probably a lot of the stuff I'm going to say will be similar to what I said in the video that went with this worksheet, but I'll try to think of other ways to explain things, and maybe just by seeing more examples that will help. Okay, so the most important thing in taking a derivative of a more complicated function, I would say, is figuring out which rule you need to apply first. I think if you can figure out what to do to get started, then you can basically just kind of use the other rules as needed along the way. And so I think that's what a lot of the challenge in this comes down to is, can you figure out what you need to do first? And so I want to look at this first example, and I'm going to contrast it with a different example that is similar but a little bit different. So let's say that we had the function g of x is equal to, and let me actually I just zoomed in, so I think now this pen is a little thick, so I'm just going to make it a little thinner. Okay, so let's say we had the function g of x is equal to sine of e to the x times x. So what's different about these two functions? Well, a few things. Notice that this one has an e to the x squared and this one just has e to the x, but that's not really the most important difference. The most important difference between these two is that if you were going to take the derivative of f of x, you would start by using the product rule. Whereas if you were taking the derivative of g of x, you would start by using the chain rule. So one thing I try to kind of emphasize in this class is getting kind of an intuitive sense of just kind of looking at a function and looking at kind of the big picture, thinking of like zooming out and looking at the function and seeing, what is really going on here on like the outermost level. And I know that's kind of abstract. I think that probably some students do well with that, but other students might find that direction is a little bit too abstract to be helpful. So another thing that you can do is just literally try to write down your function as either a product, a composition, or a quotient. So for example, this first function f of x, we could write f of x as the product of two functions, right? We could write f of x as, let's call them h of x times k of x, where h of x is equal to e to the x squared and k of x is equal to sine of x, right? Like literally you can come up with two different functions that when you multiply them together, you get your function. And so because we're linking these two functions together with multiplication, that's what tells us that this is a product and we need to start by using the product rule. And so I'll go through this example in more detail in a second, but again, the most important thing is deciding what you're going to do first. And so in this case, because we can find two functions that when you multiply them together, you get f of x. That's what tells us it's a product. So let's see what happens if we try to do something similar over here. So if you were to try to find two different functions that when you multiply them together, you get g of x, you just wouldn't be able to do it. You might guess like, okay, maybe g of x is equal to h of x times k of x, where maybe you'd guess, okay, h of x is equal to sine of x, and maybe you'd guess k of x is equal to e to the x. But that doesn't work, right? Because if you multiply those two things together, you would get sine of x times e to the x, not sine of e to the x times x. Or maybe you would guess, okay, let's try sine and sine. So let's do sine of x and sine of e to the x. But again, if you multiply those things together, you get sine of x times sine of e to the x. And that's not what we're looking for either. So as hard as you can try, you're never going to find two functions that when you multiply those two functions together, you get g of x. They just don't exist. You can't do it unless like you did, the original function and then the other function as like 1. But that isn't really a helpful way to break it down. So because we cannot express this as the product of two functions, you would not use the product rule first in this example. So what is this example? Well, this example is a composite function. So in this case, we would say, okay, actually g of x is equal to h of k of x, right? It's a composite function. And what would the functions be in this case? Well, the outer function, let's use u as we have been doing in this class, the outer function would be sine of u. And then the inner function would be e to the x times x. So notice there is a product here, right? This is a product. And so you will eventually use the product rule, but you wouldn't do it first. The first rule you use is going to be based upon what your function as a whole can be expressed as. So if as a whole your function can be expressed as a product, then you use the product rule first. In this case, how did we express it as a whole? It was a composite function, right? We had an outer and an inner function. And so that tells us that in this case, the first thing we would do is we would use the chain rule. Okay, so I just wanted to show you that other example to kind of contrast it. Let's now actually go through and see what the derivative would be in this case. So we would start by using the product rule, right? And so we would say, okay, f prime of x is equal to, and so this is where, again, that placeholder notation I think is really useful. So how does the product rule work? Well, you're supposed to take the derivative of the first function. So I'm going to write e to the x squared prime times sine of x. And then to that, we're supposed to add, now we take the derivative of the second function. So I'll say sine of x prime times e to the x squared. Okay, so now that you have this written down as your first step, now you have like the basic outline of what this derivative is going to look like. And now it's just up to filling in whatever else we need. And so in this case, notice that to take the derivative of e to the x squared, that is a composite function. So the function e to the x squared, sorry, let me make this thinner. So e to the x squared is a composite function. And so let's actually write down the inner and outer function. And again, I would kind of encourage you to step away as you become more comfortable from this, because it's just going to get kind of clunky having to name, we already said h and k, now we need two more functions. Like it's just going to be kind of clunky to continually have to come up with new functions. But just to kind of be as explicit as possible, let's actually do that. So what would the inner and outer functions here be? Well, maybe I'll call it L as the outer function. So L of u would be the outer function, and that would be e to the u. And the inner function would be, let's call it m of x, would be x squared. And so what would the derivative of e to the x squared be? Well, we would start by taking the outer derivative. So what's the derivative of e to the u? It's just e to the u. And then instead of putting u there, we just put the original input back in. So it's e to the x squared. And then we have to multiply that with the derivative of x squared, which is 2x. So now that we have the derivative of e to the x squared, now we can go and put that back into the context of our overall derivative. So our overall derivative, we were supposed to take the derivative of e to the x squared, and we got 2x e to the x squared. And then we multiply that with sine of x. And then we take the derivative of sine of x, which is cosine of x, and we multiply that with e to the x squared. And that would be our answer. Okay, so let's look at the next one. I want to focus on, like the main thing I want to focus on as I go over these is identifying how to get started. And then I will also go over the actual derivative, but I'll probably not spend quite as much time on that just because the answers are on this worksheet. So you can see what the actual derivative came out to be, but I really want to just focus on the thought process that goes into kind of selecting how to get started. Okay, so this function, we can see that there's division going on, right? We can see that there's going to be a quotient rule somewhere. We also see that there's an x squared inside of cosine, which tells us that we're going to at some point have to also use the chain rule. So how do we know what to do first? Well, we want to see, can we write this as a quotient of two functions? And if not, then we can't start by using the quotient rule. But in this case, we can, right? So we can write this function as, y is equal to, maybe we can just use f and g. So y is equal to f of x over g of x, where f of x is equal to e to the x, and g of x is equal to cosine of x squared. Right? Like if you take those two functions, f and g, and divide them, you get e to the x over cosine of x squared. So let's come back and do that derivative in a second. I want to contrast this with the function below, which has some other differences, but I think it's a good example to contrast with the one up here. So this one, it turns out that the first step we're going to do is actually not going to be the quotient rule. We do eventually have to use the quotient rule, but we're not going to do it first. And so how do we know that we're not going to do it first? Well, let's try to describe this function as a quotient of two functions. So let's try to come up with two functions. Maybe let's call them f of x and h of x. So you might guess, okay, maybe the top function is tangent of e to the x, and maybe the bottom function is x, let's say. So that might be a guess that you'd make at how you could write this as a quotient. But if you tried to put those together, you would get tangent of e to the x over x, which is not our function, right? Our function is tangent of e to the x over x. And so, maybe again, you would guess something like, okay, let's try tangent of x. But again, that wouldn't give you the right function. That would give you tangent of e to the x over tangent of x. So you cannot write this as a quotient of two functions. I suppose you could write it as sine of e to the x over cosine of e to the x over x, but that wouldn't really help you. Like the whole point in this first step of kind of breaking it down is that you want the functions that you're breaking it down into to be simpler than the original one, right? So like looking up here, we started with this function that was a fraction, and we're breaking it into these two kind of simpler pieces. And so that's really our goal with these problems. And so even if you could find a way to write this as a fraction, it wouldn't be helpful. It wouldn't be in a way that's actually breaking it into simpler pieces. So this does not work. This one, we're not going to start with the quotient rule. So what would you want to do in this case? Well, looking at this function, maybe let's just like visually talk about the difference between these two. So notice that on this one, the fraction bar goes all the way across. So we truly have like one thing on the top and one thing on the bottom. This one, we have a fraction bar, but if you kind of look a step further out, really what's on the outside of this function is tangent, right? So like before the division happens, what's really happening is tangent. That's kind of the outermost part of this function. And so we're going to actually write this as a composition. So this function can be written as, maybe let's call them f and h, I guess. So this can be written as f of h of x, where the outer function is tangent, and the inner function, actually I'll write it here, is e to the x over x. Right? Because if you were to take, think back to being in a pre-calculus class where you're asked to compose these two functions. If someone asked you to compose these two functions, you would, sorry, this was supposed to be h. You would take h of x and you would plug it into f of u, and you would end up with tangent of e to the x over x, which is exactly what we have. And so this is a composite function. So when we come back to this one, we'll be starting by using the chain rule. Okay, so let's go through this. We're going to go back to B now that we kind of saw the contrast between these two. So on B, we can start by applying the quotient rule, right? Because it's a quotient, that's what tells us to get started with the quotient rule. So we would say y prime is equal to, and again, I'm going to use that kind of placeholder notation. So we would take the derivative of the numerator, multiply that with the denominator without taking the derivative. Then from that, we will subtract taking the derivative of the denominator and multiplying that with the numerator. And then we're going to divide that whole thing by cosine of x squared. Okay, so now we can go through, now that we have this kind of framework set up, now we can go through and take some more derivatives. So we know that the derivative of e to the x is just e to the x. So this first part is just going to be e to the x times cosine of x squared. And then when we get to the next part, cosine of x squared, this is a composite function, right? And so to take the derivative of it, we need to use the chain rule. So cosine of x squared is composite with the outer function being f. I'm just going to reuse f even though we've already used it. Actually, maybe I won't. I'll use, what have I not used yet? H and k. So the outer function here would be cosine of u, and the inner function would be x squared. And so what's the derivative of cosine of x squared? Well, the outside part, we take the derivative of cosine. So the derivative of cosine is negative sine. So we're going to have minus negative sine of, and then we put our original input back in, so x squared. And then we multiply that with the derivative of x squared, which is 2x. And then from here, we need to multiply this with e to the x. So all I did was I just replaced where I had originally written cosine of x squared prime, I replaced that with the derivative of cosine of x squared. And in order to find that derivative, we did have to use the chain rule. And then the denominator is cosine squared of x squared. And then you can take it from here with simplifying it. I'm running out of space and I don't think that's the best use of our time in this video. But one thing I just want to point out that I think can be a little additional source of confusion, notice that at this place, we never took the derivative of cosine of x squared, right? So you're only using the chain rule at the specific moments when you're actually taking the derivative of cosine of x squared. And that's why this placeholder notation can be so useful, because it really helps you see what parts you are taking derivatives and what parts you aren't, right? So the way the quotient rule part works is that you're only taking the derivative of the denominator in this one spot. That's the only place the derivative of the denominator is ever happening. So that's the only place you had to actually use the chain rule. Okay, so let's look at this example. So this one, as we mentioned, is a composite function on the outside, right? So because this is a composite function, that's what tells us that we want to start by using the chain rule. Okay, so how does the chain rule work? Well, we want to start by taking the derivative of the outside function, so f prime of u, but then we're going to put actually the original inside function back in, so f prime of h of x, and then we're going to multiply that by the derivative of h of x. Okay, so what is the derivative of f of u? Well, the derivative of tangent is secant squared, right? So for this part here, the derivative is going to be secant squared of, and then instead of writing u, we'll put our original input back in. So that's how the chain rule always works, right? When you do the chain rule, you're doing the outside part of the derivative, but you don't want to have a u in your function. So you have to make sure that you're putting back your original input inside of it. Okay, so that's the outside part of the derivative. Now let's focus on the inside part of the derivative. So h prime of x, that means that we're taking the derivative of this function here. But this is a quotient, right? So we have to actually use the quotient rule in order to take the derivative of this. And so what is h prime of x? Well, if we apply the quotient rule, we're going to take the derivative of the top, which is e to the x. So I'm not going to use the placeholder notation here because it's a simpler quotient, right? The placeholder notation I think is more useful when you're dealing with a quotient where the functions are not so straightforward, where you can't just like quickly find the derivative of the numerator or denominator. So the derivative of the numerator is e to the x, and then we just multiply that with the denominator. And then from that, we subtract the derivative of the denominator, which is 1, times the numerator, which is e to the x. And then that's all over x squared. So nicer way to write that would be x e to the x minus e to the x all over x squared. And so that's what we're going to put in now for the second part of the chain rule. And probably going to run out of space a little bit here, but basically I just want to take this fraction and multiply it with what we found above. And you could put parentheses around it, I think, and I probably did. Let's see how I wrote it in the solutions. I guess I didn't, so yeah, never mind. I think if you put parentheses around it, it makes it a little more confusing looking because it kind of looks like you're taking secant squared of that part. Really just, understand that this part is you're taking a trig function of something. The other part is just some other algebraic expression that you're multiplying with secant squared. So you can basically leave it like that. It looks like in the solutions I factored out an e to the x. You could do that if you wanted to. You don't have to though. So again, the theme here is always figuring out what to do first and writing down that first part as your structure. And once you have that structure in place, I think it just becomes a lot easier to fill in the other pieces as you go. Okay, so let's look at D. So D, similarly, is, well, actually, let's pause for a second. So what is going on here? Well, it's definitely not a product of two functions. I mean, actually, sorry, I take that back. You could if you wanted to. That's not how I'm going to approach it. But if you wanted to, you actually could write this as a product of two functions. So you could say this is f of x times g of x, where f of x is equal to cosine of square root of x, and g of x is equal to also cosine of square root of x, right? Because if you're squaring cosine, that just means you're multiplying it with itself. So if you wanted to, and this is true anytime you have sine squared or cosine squared or any function squared, if you want to, you can actually do it with the product rule. I'm not going to do it that way in this video because I think the other way is kind of a better, a better kind of more general approach to understand. But if you wanted to, you definitely could do this as a product rule. So I kind of misspoke when I just said it wasn't a product, but the way I want to look at this is I want to think of this as a composite function. So what would the inner and outer functions be if this was a composite function? Well, if we have y is equal to cosine squared of square root of x, we want to have an inner and an outer function. Well, literally what's on the outside here is cosine squared, right? So the outer function is going to be cosine squared of u. And then what is the inner function? The inner function would be square root of x. Okay, so let's start to write down the chain rule because this is, right, a composite function. And one thing you might notice is that this function is actually still a composite function. So what that means is that we're going to have to apply the chain rule again, but let's not worry about that yet. The first thing we want to do is kind of write down what the structure of the chain rule looks like on the outermost level. So on the outermost level, really what we're doing here is we're going to be doing f prime of g of x times g prime of x, right? That's how the chain rule works. Okay, so now let's figure out what f prime of g of x is. And so in this case, because this is a composite function itself, that's going to take a little more work. So let's kind of do that off to the side. So let's start by figuring out what f prime of u is equal to, because that's going to be the easier thing to find. And then once we have that, we can just put g of x back inside of it. Okay, so to find f prime of u, let's actually rewrite cosine squared of u. Let's rewrite it as cosine of u squared. So what are the inner and outer functions for this function? Well, let's see, what letters have we not used? Let's use h and k. So the outer function would be, and actually we need a different letter than u. This is why it gets a little confusing to have to explicitly write these down every time. So I'm going to use a different letter other than u because the outer function is supposed to have a different letter. So I'll just say, let's say t. So the outer function here would be t squared. And then what would the inner function be? It would be cosine. So what would the derivative of this function be? Well, we would first want to take the derivative of the outside function. So we'd want to do h prime of k of u. And then we want to multiply that with k prime of u. And I think this is probably making it more confusing than it needs to be with all these different letters and different functions, but it's just the way the chain rule always works, right? We're always finding our outer derivative first and then multiplying with the inner derivative. So what is the outer derivative in this case? Well, it would be 2 times cosine of u, right? Because it would be 2t would be the derivative of t squared, but instead of putting t there, we want to put our original inside function. So it would be 2 times cosine of u. Then we want to multiply by the derivative of the inside function. So the inside function in this case is cosine of u. And so the derivative would be negative sine of u. Okay, so altogether, that chain rule that we applied to cosine squared of u is negative 2 cosine of u times sine of u. So that's f prime of u. But remember, we were not looking for f prime of u. We were looking for f prime of g of x. So that means that now that we have that derivative, we need to put g of x back inside. And so altogether, that's going to give us the same thing that we had written down over there, but we're going to now put the square root back in. Then we want to multiply that with g prime of x. So what was g prime of x? Well, that was just the original inside function. And so the derivative of square root of x is 1 over 2 root x. And so our final answer is going to be, we can rewrite this as, so the 2's are actually going to cancel out. So we'll have negative cosine of square root of x times sine of square root of x, all divided by square root of x. So I think this one, there's something tricky about this. I think it's trickier than it maybe initially looks, but it's really just kind of following this logic of doing the outermost derivative first, multiplying by the inner derivative, and then the only kind of funny thing that happened along the way is that in order to find the derivative of the outside function, we actually had to use the chain rule again. And so I think, again, I personally think that all of this is a little confusing. The way that I like to think about taking a derivative of something like cosine of u squared, I literally picture that you're bringing that 2 down the same way that you normally do with the product rule, or sorry, the power rule. And I picture that being the outside part. And then I picture, okay, now we just multiply by the inside derivative. So you don't have to write all this stuff down. I like to kind of show it both ways because I know there's some students who just really want to concretely see every single step written out with algebra. So I like to kind of show both ways. But if you found that part confusing, you can just kind of disregard it if you can just sort of understand where this came from without having to write all that stuff down. Okay, so let's look at a couple more examples. So this next one, let's try to figure out what kind of function this is. So we can see that there's multiplication going on, right? There's x cubed times e to the x. However, that multiplication is happening inside of the cosine. So we would not be able to write this function down as a product of two things, right? Like you couldn't, for example, say, h of x is equal to f of x times g of x, where f of x is equal to cosine of x cubed and g of x is equal to e to the x. That wouldn't work, right? Because that would give you cosine of x cubed times e to the x, where the e to the x is on the outside. And we want to make sure that that multiplication is happening inside of the cosine. And so what's really going on here is that we have a composite function. And again, it's just kind of like, what is like the most outer thing happening on this function? And it's cosine, right? That is on the very outside of this function, cosine is happening. So cosine is happening further out, like literally just visually looking at the function. The cosine is on the outside, whereas the product is on the inside. And so instead, we would want to say, okay, this function is a composite function. And so our outer function would be cosine of u, and our inner function would be x cubed times e to the x. And so notice that this is a product. And so what that means is that when we go to find the derivative of g of x, we're going to have to use the product rule. But let's first start by writing down, and actually, to be consistent with my color, I'll use a different color over there. We first want to start with what this function is on the outermost level. So this is a composite function. And so that tells us we want to start with the chain rule. So the first part of this derivative is going to be, again, f prime of g of x times g prime of x. And so what is f prime of u? Well, f prime of u would be negative sine of u, but we want to put back inside our original input, right, g of x. So it should be negative sine of x cubed times e to the x. Then we want to multiply that with g prime of x, but to find g prime of x, we need to use the product rule, right? Because we can see that g prime of x, g of x is a product. So to find the derivative of this, we would have to say g prime of x is equal to, so we take the derivative of the first term, which is 3x squared, multiply that with the second term, and then to that we add the derivative of the second term times the first term. And so putting these together, that tells us that the second part of our chain rule is going to be 3x squared e to the x plus e to the x, x cubed. Okay, so last one. So in this case, we have division happening, right? We can see that cosine of x is getting divided by x. However, that is not the outermost thing happening in this function, right? If we were to try to write this as a fraction, it just wouldn't work. Like you could guess, maybe f of x is equal to e to the cosine of x and g of x is equal to x, but that would give you, if you divided those, e to the cosine of x over x, which isn't what we want, right? We want the over x to be in the exponent. So this is not on its outermost level a quotient. So what is it? Well, it's a composite function. Anytime you have e, or any other number for that matter, raised to anything that's not just x, it's going to be a chain rule where the outer function is going to be e to the u. So here we're going to have f of g of x, where the outer function is e to the u, and the inner function is cosine of x over x. So notice that cosine of x over x, this is a quotient. So we are eventually going to have to use the quotient rule, but it's not what we're doing first, because overall, this function is a composite function. And so that tells us we need to start by using the chain rule. So the chain rule says that we're going to take the outside derivative first. So we have f prime of g of x, and then we're going to multiply that with the inside derivative. And so in this case, if the outside function is e to the u, well, f prime of u is just still e to the u. And so in this case, it's not e to the u, it's e to the cosine of x over x. And one thing I've mentioned, I think in some of my earlier videos that is good to keep in mind is that anytime you're doing the chain rule with e to a power, the first part of the chain rule is just gonna copy your identical function again. Like the original function will always be part of the derivative. Then we want to multiply this by g prime of x, but to find g prime of x, that's where we need to use the quotient rule, right? Because we saw that g of x is a quotient. And so how do we find the derivative of g of x? Well, we would take the derivative of the top, which is negative sine of x, multiply that with the bottom, and from that subtract the derivative of the bottom, which is 1, times the top, which is cosine of x, and all divided by x squared. So in other words, we have negative x sine of x minus cosine of x all over x squared. And so now we can put that in as the second part of our chain rule. And that's it. So yeah, so I guess hopefully this was helpful, just seeing some more examples. But if you're someone who has trouble just looking at these and eyeballing it and figuring out what rule to use first, I would just try to like literally write it down as either a composite function, a product, or a quotient, and see if you can explicitly name what those functions are. What's the outer and inner function? Or if it's a product, what are the two functions that are getting multiplied? If it's a quotient, what are the two functions that are getting divided? If you can't explicitly name what those functions are, then you're probably not starting with the correct rule. So you might need to think, okay, maybe this isn't a quotient, maybe this is a composite function, and then try to write it instead as a composite function with an inner and an outer function. All right, hopefully this was helpful. Definitely, as always, don't hesitate to come to office hours or ask me if you have any further questions.